I'm going to have something on Thursday to show you. It's not going to be on the quiz, so I can wait until Thursday. But there's something new, and it's a analysis technique that, for whatever reason, the people on the College Board have developed a love affair with. And they, for whatever reason, have vowed to put it on every single AP exam. I don't know why. It was a technique that I had never, ever heard of when I was in school, in college even, doing a chemistry major. It's called Photoelectron Spectroscopy. Somehow it has become the chic thing. So now you're stuck learning about it, I should say. That'll be on Thursday. It will not take the whole hour. It will not even take half of the hour, but I do need to show you that. All right. So taking my periodic properties, if I had to take one topic that I... Oh, that's okay. It's all right. No problem. If I had to pick one of my least favorites in this course, really as a chemistry teacher and everything that I do, it's this. Not because this is terrible, but it's dry. And it's my second favorite thing to do, where everything else that we cover is all tied for first.
Okay.
Yeah, I don't know. Like bonding, I don't mind bonding. Bonding is kind of dry to me too, but the periodic properties, it's like walking through mud to me. So I'm going to do the best I can, and frankly, I just try to keep moving and tell me if I need to slow down because I just try to get through it. Boring to me. So let's go ahead and take this on. Maybe I shouldn't tell you this until after we're done with it, but I can be upfront with you and just share that with you. So if you fall asleep, I'll understand. You are not really much of a sleeping class, except for Jane. Jane falls asleep, but everybody else is pretty good. In fifth hour, right after lunch, people are more tired, and it's not. I'm not mad about it. I get it.
Okay, I videoed.
Oh, Johnny has fallen asleep in here too.
Oh. And then I put it on Snapchat, like 200 people saw it.
Yeah, that was great. I got so many screenshots of my face, and I didn't even know if you put it on.
I love social media. I still
Nice.
have it.
Yeah.
You want to see it?
I'd love to sometime.
Okay.
Yeah. All right, so I'm going to start. So we have all these periodic properties. We have ionization energy, and then electron affinity is the second one that I'll do, atomic radius, electron negativity, and finally ionic radius. I don't know if that's, I miscounted my fingers, but we have a bunch of things to go through. And as we go through the first couple, they take a long time, but then it goes real fast. Ionization energy. Obviously, I don't want you to copy the graph. We don't have time for that. But you can always download this, or you can look in the book. The graph of this in the book is pretty much the same thing. This graph only goes up to atomic number 20, but we can definitely see a trend for what is happening with ionization energy. First of all, the definition of it. And there's one word in here that you might just gloss over and not pay much attention to, but you do want to pay attention to it. And that word is gaseous. When we try to determine the ionization energy of an atom, we are not running chemical reactions with test tubes and Bunsen burners and hot plates, things like that. You can't determine how much energy it takes to remove. We don't set up like a coffee cup calorimetry experiment to see, okay, now inside of our reaction, somebody's going to lose an electron, and we'll take a water measurement of how much energy or heat is left. No, it is a measure of heat or energy, but you can't do it with chemistry. What they do is they take, it really is a physics topic. Physicists will take atoms and they need to vaporize them. It's got to be a gaseous atom. So you've got to have, even elements that are normally solids like sodium or aluminum or whatever, you need to vaporize those things, get them in this chamber in the gas phase, and then they'll shine specific wavelengths of light at it. And the different wavelengths of light will have certain corresponding energies, and so they'll shine it with light and see if it ionizes, try a new light, see if that ionizes it, try a new light, see if one of the forms of light is going to ionize it, and then you can determine how much energy it took from what the wavelength of light was. Yeah?
What is ground state?
Ground state is where all the electrons in the atom are in their lowest possible energy. You know how we did the thing with the arrows, and we always start from the bottom, start with 1s, and do it? As long as all the electrons are in their lowest energy, then that's a true measure of the ionization. Yeah. Okay. So just a little, still an introduction. A low ionization energy means that an electron comes out very easily. Low ionization energy means it doesn't take much energy to remove an electron. Whereas a high ionization energy means it's very difficult to remove an electron. It takes a lot of energy to do that. So I've given you the graphs of them on all these slides so that we can at least look and analyze and see if we can make some generalizations about who has low and who has high. Let's take a look at the very obvious, the three elements with the highest ionization energy. It's obvious that helium is the highest, neon is the second highest, and then the third highest, actually it looks like it's fluorine, but we'll just pretend that fluorine's not that high right now. Helium, neon, argon, it should be very clear where they are on the periodic table, and it should make sense. It would be the most difficult to remove electrons from the noble gases. The electrons in the noble gases are in a very stable arrangement. All electrons and orbitals are paired up. The energy level is full. This is the way that other atoms envy, and they try to make arrangements of their electrons so they're like the noble gases. What elements are the lowest in ionization energy? Well, they'd be at the bottom of all these: lithium, sodium, potassium. The group 1 elements, yeah, right after the noble gas. So we have a general increase across the row, and as soon as you get to the end of the row, it crashes down low again, real low ionization energy. Then it kind of creeps up again. You do see that we have some exceptions. We'll have to talk about those exceptions. You read about those exceptions in the reading assignment, though, didn't you? You did, yep. And you can bet that in the end of the chapter exercises, the Zoom dolls are going to take every opportunity they can to ask you about those exceptions. They want to, of course, they'll ask you about the general trends, but you'll need to know those exceptions too. That drop right there, and that drop right there. And then corresponding, in the next row of the periodic table, you get another drop, and then this one starts to kind of level off. We'll have to address why that is too. Phosphorus is right underneath the nitrogen, sulfur is underneath the oxygen, but we don't have such a sharp drop in the phosphorus-sulfur. However, I think this graph is actually kind of bad. There is a drop. If you look in the Zumdahl book, maybe you remember this, the phosphorus-sulfur transition is not that even. The sulfur is lower in ionization energy. So for at least those two families, they, those two elements. Two meaning the nitrogen and the phosphorus. The nitrogen has a drop after it, phosphorus has a drop after it. And then they start continuing the trend again. Okay, now I had something under the shade. I'm not going to bother because it was very basic. Let's take a look at this. This is just like in the reading quiz, which, Amber, you'll have a different reading quiz, so I don't mind saying that. Carol and Kevin, this is for you. Let's take a look at the successive ionization energies of a couple of atoms. We all right back there? All right. Every time you need to remove an electron, it's going to get more difficult than the time before. And when I say that, I'm talking about for an element, like magnesium. Magnesium has 12 electrons. You can pluck those electrons off one by one if you want to. There's a certain technique. It's called, usually it's X-ray diffraction, I think, for ionization energy. So the first electron that you remove from magnesium, from a neutral magnesium atom, would take 730 kilojoules per mole of magnesium. Then it's a magnesium positive 1 ion. Now we have the magnesium atom has kind of shrunk down some because it has one less electron for the nucleus to hold on to. So the nucleus draws the outer electrons a little bit closer into it. Now try to take another electron off. It always takes more energy to take the second one off than the first. So it takes about twice as much energy. Then from the second to the third, now we have a magnesium +2 ion. And when you look at the periodic table, a magnesium +2 should kind of get your juices flowing, right? That would be a normal magnesium ion. Now try to take another electron off. It's going to make a magnesium +3. The magnesium +2 had a noble gas electron arrangement. Now we're on trying to take an electron off of that. You see this jump is about 5 times more. This energy is about 5 times more than that one. You get this exceptional high jump. Look at for the aluminum. Aluminum now has to lose 3 electrons for it to get to a noble gas configuration. So the first electron is not very hard to take off. The second electron, that takes roughly 3 times more energy. And the third electron even, it takes more energy, but a modest amount. And then when we go from the third, where it's an aluminum +3 ion, to take another electron off, it's going to take another 5 times more energy or so. So this is a very common kind of question on standardized tests in chemistry. This successive ionization energy kind of thing. Yeah?
But so, like, if you try to take an electron off, like, the row next to the noble gases, what would happen to the
like the fluorine, chlorine, the halogen family? You can remove an electron off of those. Now, those are real small atoms, and we're going to find that as atoms get real small, it's more difficult to remove an electron, because the whole reason that they're small is because the nucleus is really hanging on to those outer electrons, and so they're drawn in very tightly. So to remove an electron is difficult. But you can get them off. It'll be a lot higher energy to take one electron off of fluorine than it is off of one of these metals.
Yeah, so it would be a bigger number.
Yes, yes it would be. Yep. Really, that corresponds with this. We talked about fluorine. Fluorine is way up here with that value to take its electron off, where magnesium is way down here. There's a big difference in those. All the metals are real, real low. And as they go over to the nonmetals, where the atoms are getting much smaller, it takes more energy to remove them. Okay, so down below this shade, I mean, again, still very basic. I don't even think it's worth writing this down. We can see that once an element gets to a noble gas configuration, it's going to take a huge amount of energy, a disproportionate amount of energy, to remove another electron off of that arrangement. And that's what we see happening right there for magnesium and right there for aluminum. Anybody have any questions about that? Okay, so now for the next couple of slides, I wanted to talk about why the trends are what they are, and we'll have to get into the exceptions too. And here's our 2 exceptions on this slide. In fact, let's just focus on why does the ionization energy go up as we go across a row? When you start a row on the periodic table, the electrons are just starting a new energy level. A new energy level means that the outer electron is kind of far from the nucleus. As we go to the right, there's more and more electrons on the outside of the atom and protons on the inside of the atom. I still remember learning about this when I was in college, or not in college, in high school. When I had my first lesson on like atomic radius and ionization energy, I remember thinking, no, as we go across a row on the periodic table, the atoms should be getting bigger because we're adding more and more particles to it. There's got to be more room for protons and more room for the electrons, and there's more neutrons too. So I thought, well, the teacher must just be backwards or mistaken. And then, of course, I had to humbly realize that I was the one that was mistaken. It was the teacher that was correct and I was wrong. What happens as we go across a row is the atoms are increasing the number of particles. The number of protons and electrons is going up. But the higher nucleus charge draws the outer electron cloud in. It's not just the individual electrons that are drawn in, it's that whole energy level that gets drawn in. Because remember, an energy level is just an electron cloud. Somewhere in there, electrons are found, but we can't really track the electron, and it's not like they need more room. There's a place designated for the electrons. It's called orbitals,